Hi, I'm Gheyath, and I'm a master's student of the IUDD program at the Bauhaus University, Weimar. In this short video, I want to give you an overview of my master thesis. The main goal of my research was to investigate the role of urban planning in flood risk reduction through the development of a computational model. In the last 2 decades, 44% of natural disasters worldwide were related to flooding. And the frequency of these flood events has actually doubled compared to the 2 decades before that. Along rapid urbanization, the main cause of such floods is poor urban planning, which leads to a higher percentage of impervious surfaces and increased stormwater runoff. This results in drainage failures, which ultimately lead to urban flooding. This has raised a greater attention to flood risk management. However, its growing complexity has made it more challenging to access by urban planners with limited hydraulic knowledge. To fill this gap, I developed an integrated computational model within a computational environment to help urban planners integrate stormwater runoff evaluation into their early decision-making process. The model consists of a step-by-step framework with multiple components, which aim to minimize stormwater runoff and maximize infiltration rates. So how does it work? Firstly, the model simulates a rainwater flow direction network, onto which it evaluates different street network layouts for terrain slope alignment. The goal here is to identify street layouts with higher slope alignment values, since such layouts allow for better planning of drainage networks and water distribution. This is shown by mapping the color values of these segments. So the more the red segments, the higher the total slope alignment for the street layout. In the next step, the runoff volume and infiltration values are calculated for each street block. This is done through integrating a specific calculation method called the curve number method, which includes multiple interrelated factors, like the block's area, its slope coefficient, and runoff and rainfall depths. And most importantly is curve number value, which varies depending on its assigned land use and soil group. This makes it possible to compare the impact of different land use strategies on runoff volume reduction. For example, here on the left, you can see a common strategy of distributing land uses according to street hierarchy. On the right, there is the same percentage of land uses, but distributed according to the block's curve number values. This distribution on the right resulted in a 20% decrease in total runoff volume, compared to that of the street hierarchy distribution. In the last step, a further reduction of runoff volume can be achieved by allocating several infiltration tools, such as planters and green roofs within the urban blocks. Finally, in my thesis, I applied the model to a development site in Addis Ababa, Ethiopia, to scrutinize its performance and effectiveness in a realistic and large-scale context. To do so, more variations of street layouts and land use distribution strategies were compared and evaluated for their impact on runoff volume reduction. Overall, the study showed that street layouts with higher slope alignment can allow for improved stormwater distribution. Also, land use distribution based on curve number value proved to have the highest impact on runoff volume reduction, in addition to the allocation of filtration tools. If you'd like to know more about my work, you can scroll down and check out my full thesis. Thank you.